So today we are going to cover one of the most important aspect of numerical simulation, domain truncations. In every simulation they play an important role. The accuracy of the results that one can get using any numerical method is greatly dependent on the domain truncation techniques. In that sense, they not only play a major role in restricting the computational domain to a finite space, but also greatly affect the accuracy of the results. So one has to really pay attention to what kind of domain truncation techniques that we are using, and also how one can improve the accuracy of those domain truncation techniques. When I introduced finite difference method, I said in 1994 it was the greatest innovation in domain truncation technique that cleared the biggest bottleneck that the finite difference method was facing. In that sense, the perfectly matched layer, otherwise called as PML, is one of the most important innovation that happened in numerical techniques in general, particularly in the finite difference method. We have talked about PML in larger aspects using simulations, so on and so forth, but we haven't looked into them using a particular example. So I am going to take the next hour or so to discuss the formulation and also to present a simulation that one can really test and try for himself and see how one can implement the PML. So the kind of PML that I am going to look into in today's module is called as uniaxial PML. Normally when one talks about PML, one talks about the Béranger PML, the classical split field formulation of PML that was brought into the finite difference technique by the French engineer called Béranger. However, the method has developed over a period of time, and due to several of those techniques that has been brought into the numerical methods, the methodology of PML itself is a vast area. So we cannot discuss each and every PML. Of course, I would like to give you some references that you can go and look, comparing PMLs and also understanding their formulation and understanding their pros and cons. In today's lecture I am going to focus on uniaxial PML, that is due to Stephen Gedney, which was published in 1996. I would like to show how one can understand the formulation of the uniaxial PML using a simple 2D Maxwell equation formulation, and also I would like to show how one can formulate that PML and implement those PML in a MATLAB environment. So that is going to be a broad area that we are going to look into. That being said, it is going to be quite an intense session, but also an interesting session, because once you get to know how to model a PML, there are so many different problems that one can really solve, and it itself is a motivation for us to get started and look into the formulation. And rest assured, I am going to be there with you step by step, discussing each and every steps and manipulation that one has to do, and also make sure that you are able to really formulate them in a MATLAB environment. So that's going to be my promise, and with that promise, let's start today's module. So let's start looking at a simple Maxwell equation in 2D. When I say Maxwell equation, I am going to focus on transverse magnetic mode. So in that sense, my magnetic field, the H components, are going to be in the XY plane, which is going to be also the plane of propagation. And my electric field is going to be in the Z direction, which is going to be in the perpendicular direction to the direction of propagation or the plane of propagation. Let's look at the equation and start step by step in the formulation. So we have got Hx, Hy and Ez. That being said, so the plane of propagation is going to be the XY plane, and the Z direction is going to be the perpendicular direction to the propagation. So if I say X is going to be the direction of propagation, and XY plane So the entire plane here is going to be the plane of propagation. Puritans might argue whether you can call this as a plane of propagation, but I would like to stick to the term. What I mean is the propagation is going to stick to the xy plane, and z is the direction that is perpendicular to both the direction of propagation and the plane of propagation. So this is going to be our setup. With that being said, so the Maxwell equation for such a setup is going to have a very simple form, which is given by the two curl equations. So we have dou t of hx is equal to minus curl of E x component. Of course we have the mu term here, and similarly the mu term multiplied by dou t of hy is equal to minus del cross E, the y term here, and epsilon dt Ez is equal to del cross h, the z term. So let us look at these individual terms step by step. So I am going to start with the E term. So the del cross E is equal to x, y and z. You have dou x, dou y. There is not going to be any variation in the z direction, we can put them to be 0, and we have 0 0 E z. So if you expand it, what you get is the x component dou y E z plus the y component minus dou x E z. So this is going to be the del cross E term, and similarly the del cross h term. So the del cross h term is going to be del cross h is equal to similarly x, y, z, dou x, dou y 0, and hx, hy 0. When you do that, what you get is the x component will be 0, y component will be 0, you get only the z component, which is given by dou x hy minus dou y hx. So now I am going to plug all these components into the equation. So what we have got is, for the first equation we take the x component, that is what I have written here. So this is going to be this term, and of course there is a minus sign, so I am going to write it as minus dou y E z. For the second one I am going to write this term, and the minus sign and minus sign gets cancelled, we get dou x E z, and for the third one this is going to be this entire term, that is equal to dou x hy minus dou y hx. So these are going to be the field components, and these field components are going to be the main elements that we are going to take for modeling the uniaxial PML. So let us look now into the uniaxial PML setup, a domain that is a rectangle. So in this kind of a domain, the uniaxial PML, or any PML for the matter of fact, has to be sitting in the way given below. You will have top and bottom PML, you will have the right and left PML. As you can see, the real computational domain is going to be the entire domain. Although the entire domain is called as the computational domain, the object of simulation will be mostly sitting in this area. So we will be keeping all the objects that we are modeling in this area, but let's look into the PML itself now. So this is going to be the domain, and what you can see is there are going to be several regions. The first region is the X oriented regions. They will be called as X PMLs. Similarly, there is going to be Y PML. So this is an X PML, this is an X PML. Similarly, Y oriented PMLs are Y PMLs, and the top PML is also a Y PML. However, there are also 4 mixed PMLs, so these regions. So I am going to mark them in black. So these are areas where we have both X and Y oriented PMLs. So why am I splitting the PML in this way is a question that needs to be answered. The reason for splitting the PML in this way is because the material composition of those regions that we are having in the PML domain are going to have a special property, and that property is called as anisotropy property. What I mean by that is, for an X oriented PML, the permittivity and permeability are going to be not a scalar quantity like epsilon or mu, but they are going to be value that is a tensor. So they are a tensor because the relative permittivity, which is given by the value epsilon divided by epsilon naught and mu divided by mu naught, is going to be a complex tensor also. So these are the relative permittivity and relative permeability. They are going to follow a pattern which is an anisotropy pattern. If it is an X oriented PML, they are going to have a form like this: 0 0 0 A 0 0 0 A. I will come to what A is, but it is important to know both the relative permittivity and the relative permeability are going to have a special form. This is for the X oriented PML. Whereas for the Y oriented PML, they are going to have a very different form. It is going to be A 0 0 0 1 by A 0 and 0 0 A. So this is going to be for the Y oriented PML. So this is going to be for the X oriented PML. As you can see, the value 1 by A is going to change its location along the leading diagonal. So with that being said, let us look into what is this A and how can we understand its implications in modeling a perfectly matched layer using the uniaxial concept. So the A value, what we call it as frequency dependent term, it is a complex value, and its value is going to be given by the equation A is equal to 1 plus sigma divided by j omega epsilon. And of course, if it is going to be an X oriented PML, it is going to have a subscript X here. If it is going to be a Y oriented PML, it is going to have a subscript for sigma as Y. So let us now look at it only from an X oriented PML point of view. We can similarly think of counterpart for Y oriented PML. So for when A is equal to 1 plus sigma x divided by j omega epsilon, where sigma x is the loss factor or loss inside the X oriented anisotropic PML. So when we have a form like that, what you also see is it is going to depend on the frequency, where omega is equal to 2 pi f. It is also going to depend on the permittivity inside that medium. So there are going to be a lot of factors. It is going to depend on the loss, it is going to depend on the frequency, it is going to depend on the permittivity. So now let us take this equation A equal to 1 plus sigma x divided by j omega epsilon and plug it inside the equation what we have got. So we will get the value for epsilon divided by epsilon naught equal to 1 by a 0 0 0 a 0 0 0 a, and that is going to also be equal to mu divided by mu naught. Do not forget epsilon double bar on the top is going to be given by epsilon naught epsilon r, where epsilon r is also a tensor, and this is the tensor what we are talking about. So now we are going to multiply this particular form to get an equation that we are going to model for the uniaxial PML. So let us plug this one into the equation what we have earlier derived and start deriving step by step the uniaxial PML formulation. We will start with the basic equation. So we have got mu dt hx equal to minus dy Ez, and I am going to plug in the value for mu. As I said, mu is now going to be a complex number, so it is going to be, so now I am going to multiply mu naught epsilon naught into 1 by a 0 0 0 a 0 0 0 a into dt multiplied by the term hx hy ez equal to the terms of the right hand side what we have got from this equation. So the first term will be going to be equal to minus dy Ez, second term is going to be dx Ez, third term is going to be dx hy minus dy hx. So what we are going to do is we are going to go step by step in deriving this equation. For example, we can start with the first equation and we can go to the second equation, so on and so forth. The first equation is exactly this equation what we have got here. So now we can write this equation in an expanded form and then see what we get. So what we get is mu naught multiplied by 1 by a dt hx equal to minus dy Ez. Similarly, the second one will be mu naught multiplied by a dt hy equal to dx Ez. The third one will be epsilon naught a dt Ez equal to dx hy minus dy hx. So you might wonder, why am I multiplying this for the Maxwell equation? So the Maxwell equation, the curl equations are only this. Why am I multiplying this particular term? I am doing that because the Maxwell equation is only valid in this domain where I have marked it as red. When we go into any of this PML domain, the Maxwell equation will follow the anisotropy model that we have accepted. So this is going to be the permittivity and permeability values. So because of this, if I have to model a PML and model the Maxwell equation in the PML, I have to inevitably start with the setup we have given here. So let's stop here. We will come back and derive the equation step by step as we have casted here, and how we can take it to a MATLAB model as we go. So this is going to be the next step. We will look at it in the next module. Thank you.